Final session of the afternoon devoted to more things that epidemiologists should know. And we start with Simon Frost.
Thank you, Dennis. I'd like to thank the organisers for being here. My first time was back in '93 as a sort of fresh-faced graduate student, but it's equally nice to see so many new faces here, and I've really enjoyed meeting you all. So today I'm going to talk about being open and fair in modelling and how we can go about that, and how actually it can make us more productive as well as just better scientists. So what do I mean by fair? Fair is a sort of principle of open science. It means your science should be findable, accessible, interoperable and reproducible. And it's becoming more a condition of grant funding that you fulfill those criteria in your work. But today I'm going to talk about going beyond fair. I've given many talks on fair principles, and in many cases, those principles can be addressed through software engineering practices, like using GitHub, Docker containers, that sort of thing. But today I'm going to dig a little deeper and talk more on the mathematical side of things and how we can make models replicable, how that we can recreate them from scratch more easily rather than just reproducible. With the idea that making complex models, their development and their role in guiding decisions should be more transparent. And Kevin Conway in his talk on Monday described this as intelligent transparency. So this is based on a new project that started just last month with two main themes: to make models more composable, where we build up complex ones from simple components, and then also to extend those models to routinely perform optimal control in terms of being able to identify effective interventions. The idea is that this would increase preparedness as well as being able to respond faster in an emergency situation. And because this grant has just started, I'm going to describe what tools developed by others can do today. So reverse engineering models is hard. And it's hard because we often only see the final product. Because in open science, you just have to be able to reproduce the results, and you can do that with a black box. Models can be complex. Michael Planck referred to his own model as Frankenstein's monster because it sort of grew up over time and got lots of compartments and so on. And it's often hard to see how a given model could be simplified, because it can be in many cases, or extended if you needed to add more compartments, more flows, and so on. But a bottom-up approach where we make complex models from simple ones is easier to understand. It also reflects the thought process during modeling, and it, when we're at school, in maths classes, we're all encouraged to show our working. We get extra points for showing our working. So can we do this when we're building models? So my colleagues at London School are part of this Epiverse Trace initiative, and they've made this very nice R package called Epidemics. And they refer to it as composable epidemic scenario modeling. And they do that because you can plug in, for a given model, demographics, different contact structures, interventions, and so on. And it will be interchanged. But this is achieved by building a single large complex model. And then if the model structure slightly changes, sometimes you have to build a new model from scratch to be able to do that. So I'd argue that the code is modular, but it's not really composable. So there's been some work over the past 5 years or so that has taken concepts from category theory, sort of an abstract branch of mathematics, to help to provide tools and formalism for us to be able to add models together and multiply models together. And I'll expand on what that means in a moment. These papers are out there. They haven't been widely adopted, and I think there are a number of barriers to that. One is that the terminology is somewhat new to many of us, resulting in a steep learning curve. And what I will try to do is give you some examples to be able to look at that. Applications of category theory or applied category theory to modeling are relatively recent development. There's a wonderful paper published in one of the Royal Society journals by Sophie Libkind et al. That gives a very good exposition of this. And also software implementations were lacking. But over the past few years, DARPA has run a program on developing models, sort of generic, not just for epidemiology, and that has provided funding to be able to develop software to be able to do what I'm going to show you. So here are a few concepts from category theory and how they could fit into epidemiology. One is, what is a category? Well, a category includes two things. It includes objects, and an object could be a different state of an individual, like susceptible or infected, and morphisms, things that change one thing to another thing. And that could be a disease process, like infection or recovery and so on. And there's a link at the bottom where I've gone through a whole bunch more of those concepts and how they could link into epidemiology. I'm going to skip over that for a second because it's got a bit too much jargon, I think. But in order to be able to apply this, I'm going to give you a concrete example. So let's take a standard SIR model, and so the diagram up on the left-hand side, that should be fairly self-explanatory. And one thing that we can do is turn it into a Petri net. That's already been mentioned, I believe, by Chris Jewell in his discussion earlier on in the week, where you represent states by circles and transitions by squares. So there you see that the square that looks like infection has arrows going from S to it and I to it, and then two arrows coming out because you have the original infected and then you have the infectee. Now, how this is represented in a sort of more categorical way is on the bottom left-hand side. It's a diagram of finite sets, and there are four types of sets. There are the states, SIR, there are transitions, T, which are infection and recovery, and then there are inputs and outputs, which essentially link everything up together. So we go from something that we can look at and looks quite nice to something down on the bottom, which is a structure that we can manipulate algebraically. So how we would go about composing models is that we first define one of those Petri nets, which we could just draw or we can write down. We create a wiring diagram, which I won't show you, but I'll give you some code for it. And then the wiring diagram guides how you build up a bigger Petri net, effectively, allowing us to add models together very easily. Just to be more specific, let's say that we have an SIR model and we want to be able to include a pathogen that is more virulent. So now our infected individuals die, or they could go to hospital and either recover or die. So this approach, where we've taken a categorical theoretical representation of these Petri nets, provides a formalism where we can glue those models together. So the standard SIR model has two types of transition, infection and recovery, and then we can essentially create a wiring diagram. The code for that is in the middle, where we just say sort of infection results from an S and an I going to an I and an I, and recovery means an I goes to an R. And then from that, we can generate that Petri net at the bottom. Now we've got an SIR model, we've got a model of hospitalization, and a model of infected mortality. And then we can make another wiring diagram where we take our original model, our SIR model, we take the hospitalization model, and we take that infected mortality model, and the formalism that allows us to take those tables of input states, output states, states and transitions, gets glued together in a predictable way. So we can now make this model. And we've got a pathway now where we've got three component models that are very simple, and we can put them together in a predictable way and make this sort of SIRH model. Where the real power of this approach comes in, though, is when you stratify models. So imagine that you've got a model with age groups, risk groups, and so on. And this is not uncommon, especially in COVID. This is one model from Gergo Berner and Sebastian Vollmer, where they have sort of a reasonably complex number of health states. They've also got states for isolation, they've got testing, and age. And you want to combine all of those things, and you end up with a very complex looking model that's very hard to inspect. So a stratification approach, basically where we're trying to multiply models together, you choose which models you want to put together, you then say how you want to combine them. So there's an additional layer of complexity, and then you generate the product of models. So I'm going to reproduce the sort of default model from this R epidemics package, which is just an age-structured SAR. I'm going to drop the V for right now, just for time. So at the top, I've got my original SAR model. At the bottom, I've got a model with 3 age groups where infection can occur within and between groups. Now, I didn't actually draw that bottom one. I've just got a function that will do that because the age structure matrices are quite simple to be able to do. And then what we have to do is, I've got an age model that says about infection, and I want to combine that with my SEIR model. But the age infection model doesn't know anything about what to do with recovery or death, that sort of thing. So we have to sort of embellish, augment those component models, and that tells us when we combine them that we should glue them up in a certain way. But again, we're doing so predictably, and the individual models are sort of quite interpretable, whereas the combined one becomes a bit of a mess, and then the slide is formatted badly intentionally. You know, if you were looking at this, then you've just got no idea what's going on. So the benefits of this, you've got a mathematical language to be able to add and multiply models. It's easy to simplify a model, to extend and swap out components, and it aids in reusability. I'm going to build a toolkit of various bits of model that you can put together. Although this field is still under very much active development. Chris Brown and Sean Wu, Sean's been a long-term collaborator, are developing algebraic versions of agent-based models, where you can imagine that stratification issue is really extreme. And then I think there's also opportunities to think about how best to represent interventions. So where we take a model, we run it for a while, and then we sort of map it into a different parameter space. And again, that fits in nicely to sort of category theoretic foundations. So mentioning interventions also allows me to spend a couple of minutes just talking about optimizing policy. There's a lot of interest in comparing different interventions. In many cases, you've got like a fixed small set of interventions that you consider. But there have been a smaller number of papers over the pandemic that used optimal control to try to identify the best intervention. Many of those, however, in order to get papers really, sort of sat down and worked through the maths using indirect methods in order to be able to identify the optimal control. And while those analytical results are preferable for many reasons, they might not be able to be easily derived on a timescale that you might need to respond to in an emergency. So I asked whether we could automate methods for doing optimal control numerically, making sure that those things are robust. So there are these sort of 2 broad classes of optimal control. There are indirect methods, which require more mathematical manipulations. And then there are the sort of ones that are simpler to implement, direct methods, where we just try to, you know, we've got some sort of curve which might represent the amount of lockdown, and we want to sort of optimize that curve. And one approach to do that is to discretize the model over time and then treat it as a nonlinear program. So what a nonlinear program is, we try to minimize, alternatively maximize some function subject to inequality and equality constraints with some bounds on the variables. So these haven't been widely used. I think there's a number of possible reasons for that. Some of these solvers are very expensive. It's not clear how to sort of fit a mathematical model, an academic model into that framework, or just a lack of awareness. And so I've done some initial exploration to see how much work it really is and whether these things are reliable or not. So we might be able to, we might be interested in reducing total infected, flattening the curve, reduce peak infected, and so on. And we might have, say, contact reduction or vaccination in our armament of interventions. So the way that I put them all together is I discretized them over time. I solved them using a free solver, getting over the cost. And then I wrote the models using a domain-specific language. It's called JUMP. its thing in Julia, but there are many alternatives that you can do in Python in sort of specialized languages like AMPL. So if we have a model where we're reducing contact rate, just a standard SAR model, then the way that we can fit that into a nonlinear program is to discretize it. So infection and recovery, we just have a long vector, and then we've got some nonlinear constraints that represent the discretized differential equations. As an aside, there's actually some nice domain-specific language work in Julia that allows you to write those models, almost like the maths, and then under the hood, the discretization is done for you. So reducing the total infected, minimize the cumulative number of cases that I put into the model, subject to an intervention being below a maximum, and that the cost of the intervention, the sum of this control variable, is less than a total one. And Tom Britton, back in OpenFolfac, presented some nice results showing that the optimal policy for this is a single bang-bang intervention, where you go from nothing to your maximum possible intervention for a single period. And this is how that gets written up in code. So the nice thing is that when we plug this into a solver, in about a second, the numerical results almost match perfectly the analytical results. And then we can do the same thing. We can just, in a very sort of composable way, we can swap out the constraints and the objectives and say, how would we flatten the curve in this one? And again, the numerical results match up, to within numerical error in doing the same thing. In this case, the optimal control is wait a bit, go up to close to the maximum, but not the maximum, and then relax until eventually you can stop the intervention. And then we can do the same thing for vaccination, which is a very different kind of curve. You want to vaccinate as early as possible until your vaccine runs out. So the overall results is that, at least these simple models, numerical results worked really well. We can sort of tweak things to make things a bit faster. All of those things that you just saw ran in about a second. And it didn't take very long for me to write some models either. There are a number of issues with solvers that I dealt with. I chose one, but other ones didn't work very well. Sometimes there are issues with models. And I also tried numbers of approaches, other than nonlinear programs, and none of them really worked that well. So perhaps I just chose well in this sort of first exploration. So to conclude, applied category theory is a promising method to compose models. Writing deterministic models and nonlinear programs can give us optimal policies, at least for these simple cases. And even when it doesn't, it might point us in the direction of analytical results and perhaps some shortcuts. And there's the potential to take ACT and apply it to the whole sort of modeling process, modeling categorical data as categorical databases, in fact, and then combining that with ACT approaches to nonlinear optimization and the modeling overall. So I'm going to leave this up on the board for a little while. All of this stuff you can find online, and I'd like to acknowledge my many collaborators, and thank you.
I take it you'll put your slides.
Slides are up. They're right there.
Oh, right. Okay.
Okay, time for a question or two. Any questions?
DJ.
Well, if there are no immediate questions, you can nod Simon after. We'll carry straight on with that.
TJ has one, but we can get to it later on.
Oh, we've got a question, right. Well, while Marianne is setting up.
Yeah, thanks for nice talk, Simon. I was just wondering if this sort of ACT kind of framework could also be, because this is obviously for generating models, which are then used to run simulation.
Yeah.
Could you conceptualise using the same framework if you wanted to embed those models within inference algorithms? So if you wanted to put your model into up to that CMC algorithm, could that framework be adjusted to do those sorts of things as well? So
Yeah, the underlying data structure is like a cross between a graph and a data frame. So it's very flexible in terms of the overall data structure. People have used it for databases, although there's a problem with querying it with multiple keys. But otherwise, for that sort of thing where you might look at, swapping in and out ABC or what variables you might use for the inference, etc. Could be, because it's a very flexible framework, but actually sort of getting it so that it's less work to do that, what you gain out of it, I think is really the important question.